Hello, this is Professor Bennett from digitalaudiotheory.com. In the next two programming examples, we will look at the discrete Fourier transform for two simple audio signals, a transient and a sinusoid. Now, the discrete Fourier transform, or DFT for short, analyzes a signal at n different frequencies, equally spaced between 0 Hz and the sampling rate fs. For a particular frequency bin, we'll call k, if that frequency is present in the signal, then the magnitude of the DFT for that signal will be large at that frequency bin, and vice versa. If that frequency is not present, it's absent from the signal, then the magnitude at that frequency bin of the DFT will be close to 0. We can determine what the DFT of a delta function, which is simply a digital impulse with the width of a single sample, we can determine what it will look like. Impulses are a preferred test stimulus in many audio applications to probe a device since they provide equal energy to all frequencies, which is to say, they have a flat magnitude response. But how does this bear out programmatically? As a quick aside, the FFT, or fast Fourier transform, is simply an efficient implementation of the DFT that removes redundant calculations. We will be using the FFT function in MATLAB and Octave, which takes two arguments, the input signal itself and the number of frequency points to analyze, n. An appropriate size for n is at least as long as the number of samples in the sequence if reconstruction of the original sequence is desired. So let's take a look at the DFT of a delta. Here, let's use just 8 points. We can change this later if we want. We're going to construct a delta, which is a 1 followed by all zeros. So here we go. D is in fact a 1 followed by zeros. And we can plot the FFT of this. So we're going to plot the absolute value of the FFT. That will give us the magnitude. There you have it. The magnitude of the DFT of the delta is indeed flat, as expected. Now, a sinusoid, on the other hand, comprises only a single frequency. Therefore, we expect its DFT to result in a spike. Actually, in a pair of spikes, one within baseband and one that is its conjugate, with the magnitude split between them. The reason for this is that it takes a sum of two complex phasors with opposite imaginary parts to create a purely real phasor. Therefore, we expect the DFT of a sinusoid to have a large magnitude at two frequency bins and zeros elsewhere. For the sake of simplicity, let's start with a cosine whose frequency falls exactly on one of the DFT bins, rather than in between them. So if there are n bins, then if the frequency is at some integer division of n, then it will fall exactly on one of the DFT bins. For example, if the sampling rate is 48 kilohertz and we perform an n equals 32 point DFT, then the frequencies of 0, 1.5K, 3, 4.5K, and so on would meet this criteria. Let's go ahead and select 6K for this programming example. And so the ratio is 4 over 32. 32 being the number of points and 4 being the bin that represents 6K at 48K sampling rate. We'll let the letter R select the numerator of this ratio inside our code. We will evaluate. Next, we know that according to Euler's theorem, a cosine can be split into two complex phasors in the form of exponentials, each with half the magnitude, but with one having opposite phase. So in other words, we can represent a cosine, a real cosine, just like this. Half the magnitude, half the magnitude. Here is our e to the minus j2 pi over n. One will be raised to the positive r times n. The other will be raised to the negative r times n. And when I say times n here, I mean little n, which is a sample index, a sample vector going from 0 to big N minus 1. Interestingly, The DFT for any given frequency bin k is also something raised to the k. So when it gets multiplied by our cosine, the r that is selecting the cosine frequency gets added to the k that is the analysis frequency of the DFT. And after just a little bit of algebra, we obtain this. Now this is laid out in more detail in the textbook, Digital Audio Theory, a Practical Guide. So, this custom DFT code has two nested loops. The outer loop iterates over all the frequency bins that are being analyzed, while the inner loop performs the summation of the analysis phasor against the signal that's being analyzed. We have to loop over the entire signal to make sure that we aren't missing any of the frequency k anywhere in the signal that's being analyzed. When we evaluate this code, we see that xk does indeed have a large magnitude spike associated with two frequency bins. They are at 4, which is the location of our 6k sinusoid, and at its conjugate. All right, so it's going to appear at the top half of the complex plane as well as somewhere in the bottom half of the complex plane. We can also see this by displaying the value of every single bin of the DFT. So at 0, 1, 2, and 3, these are all very close to 0. As soon as we get to bin 4, all of a sudden we have a large spike. Now remember, this cosine had an amplitude of 1. And since we're analyzing at 32 discrete points, the magnitude is going to be split. That 32 is going to be split between k equals 4 and k equals 28, which is our n, 32, minus our r, 4. That gets us down to 28. So each of these two locations receives half of the magnitude. In the next programming example, we'll look at what happens when a frequency falls between two DFT bins. I hope you enjoyed this. Thanks for watching.